Hello everyone, this is Chris from Visual Components, and today we are going to have a deep dive in the KUKA.sim add-on for Visual Components Premium and Premium OLP. This video focuses on robot programmers and commissioners that are using robot with the KUKA robot language KRL in the simulation Visual Components Premium. In this video, we are first going to enable the KUKA.sim add-on. Then, after a restart, we will use the KUKA RCS, so Robot Controller Simulator module, to write a KRL program and get cycle time calculation and expert programming. We will then have a closer look at the trace feature for KUKA robots and optimize the robot movement with that. In the end, we are going to export the program to KUKA Work Visual so that the robot can be commissioned. So let's get started. We first are going to activate the KUKA Sim add-on. For that, we have to go to the File tab, Options, Add-on, and enable the add-on. A restart would be required. So we're going to press OK, then back on File and Exit. Now that we have restarted the application, we have to check on the KUKA system software or KSS version. For that, we need to go to the File tab, to the Options, and in general, if you scroll down, you'll find the default controller configuration, and here you can select your supply voltage or also the controller version. In this case, you can select between different KSS versions. So here, if you take KSS 8.6 or older, you can select a KUKA controller of the 4th generation. And if you select a 8.7, you can load a KRC5 controller into the simulation. If you plan to transfer the KUKA robot language program or KRL program to a real robot after the offline programming, it is crucial that you use the right KSS version here as on your real robot. Now let's take the 8.74 and select OK. Great. Now, as we are back in the Home tab, we are going to pick some components from the eCatalog, and we'll go to Components, scroll down to KUKA, go to the Robots, High Payloads, and the QuantDeck. I'm going to make the window a little bit wider. And then if I now double click on the KR120, it will generate in the origin of my simulation world. In this case, the KR120 stands for a payload of 120 kilograms and a reach of 2700 millimeter, and it's the 2nd generation of the robot. You will see that next to the robot, it also adds the controller from the version that we took before, so in this case a KRC5 controller, into our simulation world. Just going to reduce the output window here so we can have a better look on the robot. We're going to need a gripper, so for that I go to the Visual Components folder, all the way down to Robot Tools, and I'm going to select the generic 3-jaw gripper. And when I drag and drop it onto my robot and let it go, it will automatically connect to the flange of the robot, as well as the signals are going to be connected. In addition to that, we will need a basic shape. And here I will select the cylinder geometry and also drag and drop it into my world. And here I will now reduce the cylinder radius to 60 millimeters. Now that we are put and ready for the next steps, we're just going to save the layout. So I go to the File tab, Save As, in my models, and just going to overwrite this last intro session. Now let's have a closer look at the robot. For that, we're going to go to the Program tab and select our robot to get to the robot properties, and we are already in the jog view, but we first want to have a look at the component properties of the robot, so we're going to select that. Here in the default tab, you can find the name of the robot, but you can rename it to whatever you want. You can have a little description, and you can see the current positions of the axes. But you can also add the 2D workspace. To showcase this, I'm going to reduce the output window again. And I'm just going to select here the 2D workspace. So there's a line shown where the robot reach is going to end. So if I go to the manipulation mode jog and click on my axis 3 and move the robot axis specific, you will see that this line ends on the wrist of the robot. Now we can follow up this line if we move axis 2. And now you will see that the axis 2 is over the limits. So I will reset it and select this stop at limits option here in the limits group. And now if I do the same thing again, if I move my axis 2 all the way down, it will stop at -5 degrees. And now I can continue with the follow-up of this little line. And you will see that it will actually be always in the wrist of the robot following the limits of the axis. I'm going to reset the simulation. And I want to show you one more thing. It's in the component properties again of the robot. You can also select workspace 3D, where it will show you a 3D bubble of the reach of the robot. So you can see if your robot is going to reach to some applications in the 3D world. I'm just going to deselect this again because it will confuse us otherwise. Now let's have a look at the accessories. Here we can add lift tools, so the pouches where the forklift can grab our robot. This might be important if you design your layout, that you can also position your robot and then remove those lift tools afterwards. We can also take off the energy supply if you have a customized one, or add it again if you want to have it visualized. And we can add a mount plate where it adds some metallic plates under the robot with some screws. Just going to deselect that again and now go to the controller tab. Here you can again select between the last version of the 8.7 KSS version. So we can go up to the 8.7.0, but we cannot proceed to a KRC4 controller anymore. This you have to do it via the options that we had a look before. In the RCS tab, we can see the key settings for the RCS module, which stands for the Robot Controller Simulation, and which is the backbone of the KUKA Sim add-on. We can disable it, and without the RCS module running, it will be just a normal Visual Components robot. But we actually want some path planning and also some cycle times, so we're going to select it here. What will happen if I have it selected and I press the play button? The robot will actually generate machine data. So as on a real robot, it will use machine data. So let me reset the simulation. And I'm going to select another tab, for example the default tab, and go back to the RCS tab to showcase you one thing. Now here in the robot data folder, there is a path written. I can have a look at this path. If I go to select this path, copy it, and then if I go to my Windows Explorer, File Explorer, I can now paste this path and I will find directly the same files or folders as you are used to on a real robot. So in this case, if I go to my KRC R1 for my first robot and machine data, I can have a look at this machine data and it will be the same as on a real robot. Be aware that if you make changes here, it might not be taken into account in the simulation. So you also have to configure it in the simulation so that it is updated. Let's go back to the settings. If I want to make some new configuration and overwrite the machine data, I have to select this robot data generation box here, and it will gray out again the path and it will overwrite this temp folder. In addition to that, if you might have some problems or errors, you can generate new ones. For that, you just have to deselect the tick in the box, select the whole path, delete it, and reactivate the robot data generation button, and then play the simulation again, and the robot will generate new machine data and create a new temporary path. Let's reset the simulation and let's have a look on the left side of our program tab windows here. So on the upper view, we do have the program structure. So here, if I right click on the program, I can add a new folder, a new program, or a new submit. But I want to show you something else. Here you can extend the program view. And if I make it a little bit bigger, you can again go or see the same structure as I just showed you. So if you go to the MADA folder and double click on this machine dot, you will see the same information as we saw before in the notepad. If I now activate again my main program and go back to the program view, so here you can switch between the DAT view and the SRC view as you are used maybe on a real robot controller, so it's the same syntax. And if I go back now to the program view, you can see that we have 2 points here, 2 home positions. We want to start with some programming now. Before we do that, we still need to do our tool and base configuration. So I'm just going to reset the robot real quick. And I will now go to the jog settings. And here I can do the tool and base configuration as you are used to on any other Visual Components robot. So I can choose one of the 32 bases and then click on the gear here to go to the settings. And you will find it displayed here in the screen. And now I can actually move it around. So I can grab it here and move it forward. And you will see that the coordinates also follow that. In the world view, of course, it's from the world simulation coordinate system. If you go to parent, you will see the same values, but it actually calculates the distance from the base to the ROB root of the robot. Let's go back to the jog settings and now select our tool. So again, here you have 16 different tools that you can configure with this little gear here. So in the settings. And here we have now our tool center point on the flange of the robot. Again, here in the world view and here kind of in relation to the flange. So I can now come and snap this TCP with the snap tool here. And I will use a 3-point snap and I will only set the position and not the orientation between my gripper jaws here. So this will be my first point. This will be the second. And this will be the third. So now my TCP is nicely positioned between the gripper jaws. And you can see that it's 124 millimeters from the flange of the robot in Z direction. We can have some other settings here, for example the mass. If there is -1 written here, then the RCS module will calculate the trajectory with the maximum payload of 120 kilograms. If we enter another value, for example 20 kilograms, which might be the mass of the gripper right now, it will change the cycle times accordingly. And here in the center of gravity and inertia, you can enter the same values as you would do it in KUKA load. In this case, I'm just going to write in some dummy values so you can see this use case. And maybe here it is 120 millimeters, and also in the inertia. Please use the same values as you get out of your CAD program and then enter the real values here. This button, calculate mass center and inertia, does not really work. If we play now the simulation, it will overwrite this TCP information and take this into account. Now that we have set our tool and our base information, we can start with the programming. So we will go back to the left side of the window and we have different options here. So after our home position, we want to move in a TCP movement. So I'm just going to grab the frame here of my robot and move it a little bit to the side, maybe somewhere like here. And now create a new point-to-point movement with this button here. And you will directly see that the syntax of the KRL program is selected. In this case, it takes into account the tool 0 and the base 0. So I'm just going to change that. I want to use my base 1 and my tool data 1. And will again touch up my point 1. And now you can see that it takes over also these two settings. Next, I want to go and snap here my little cylinder geometry. So I'm going to select the snap option, go to the 1 point method. I will also set the orientation and now select the top of the cylinder, and you can see the robot directly jumps here. And now I can still adapt a little bit the points so that it really grasps also the part, go a little bit down, something like that, and create a linear movement to this point. The last thing I want to do is to showcase you the circular movement. So I want the robot to go all the way here with a circular motion. So I'm just going to click on this circ motion. And it actually creates 2 points, so the point 3 and the point 4. If we have a look at the frames of the robot, it created a third point, the point 3 here. And the point 4 is my endpoint. So this is not actually what I wanted. I wanted to have the point 3 somewhere like here. So I'm just going to move the robot up here and then right click on the circ movement and touch up the auxiliary point. So now the point 3 actually jumped here in the middle between point 2 and point 4. Great. Now, if I play the program, we can check out what the robot is doing. Goes to point 1 to point 2, makes the circular motion and goes back into the home position. Great. You can see that here next to every statement and movement there is already a cycle time written down. So you could now look at it and sum it up and you will have the same cycle time as on your real robot or with using a real controller. But in addition to that, we can add also a timer. For this, we will select the home position where we want to start the timer. Go to this miscellaneous drop-down menu and select a timer. In addition to that, we're going to add the timer off statement after the last home position. So when we are finished with our cycle, and add another timer. Be sure that they have the same number if you want to refer to the same timer. And here we want to go now to the statement properties and switch it off. If we now play the program, it will again make the exact same path as a real robot, and it will calculate us our first cycle time, which is now 4.74 seconds. And you can see also the information about the robot motion and the name of the robot. So this is how you can easily calculate cycle times in your program with this KRL language. Now we want to change a little bit the settings of the point. So for example, if we go to the point 1, in the statement properties, we want to blend over the last point, so make a continuous movement that the robot doesn't stop there. So if I go here to standard, it will add me an approximation distance, which distance it will maximum take to blend over this point. And I want to reduce the speed of this linear movement to 0.5 meters per second while traveling down. Let's see what happens. So you can see how this cycle time drastically changed and is now way longer because I have a way slower path or linear motion from P1 to P2. Now I want actually to pick up the cylinder that we placed in the simulation at the beginning. For that I have to have a little look at our signals that are currently connected. If I go to this signals button here in the connect group, I can select my robot, and here I can select between the different signals. Where I click on this little arrow to the out signals, and I also see that there is a lot of out values already predefined. So from out 1 to out 16, it will be a grasp and release predefined for different tool datas. Then if we continue from out 16 to out 32, we have traces for those TCP or tool data values. From out 33 to out 48, we have an mount or unmount tool signal. From the signal out 49 to out 80, we have a trace for the base. And last but not least, the out 81 gives us the swept volume of the whole robot and the system. Then if we proceed, we still have the out 100 for the action of the generic gripper, and the out 101 is kind of the different signals, so open or close. These are predefined as we snap the robot to the gripper. Now let's use those signals. Let's have a further look at the input signals. So if I double click here on the little arrow, we can see that we have the in signal 101 for the open state and the in signal 102 for the closed state. Now I can close this little window, and I will now go to my point number 2. And after this point number 2, first I want to grasp the part in my simulation. So I go here to this logic drop-down menu, go to inputs, outputs, and set an output. So now if I go here to the statement property of the statement, I will find that I use my output 1, so set it to true, and this will enable me this grasp action with my tool number 1. After my point 4, I want to release this part. So again, I will go to logic, go to my in and outputs, set an output, and I will now write here as a value false. This is not case sensitive, but you have to write false in it. And when I play now the simulation, it moves my part. And if I now go back to my home position, I can now add some other signals, for example, that the gripper actually closes. It's the same procedure. So after this out 1, I will now set the signal to the movement of the gripper, so set output. And you might remember it was the signal number 100. And if I set it to true, it will do the action for my 3-jaw gripper. Then I will add another statement. It will be wait for, because I want to wait until I get the right signal that the gripper is closed. And if you remember it correctly, it was the signal 102. And I will do the same thing after my output number 1, which is false. I can copy this statement, add it again under my output 1, and here write again false. And now play again the simulation. And you will now see that our cycle time changed. So with this wait for signal, we have now added a time of 0.38 seconds to our cycle time. In addition to that, we can add a wait sec, which is here in miscellaneous. And we add this wait a sec and can add 1 second. I'm just going to use that to showcase you one thing. That if I now go down, this is already known. We will grasp our part and bring it to 0.4. And now we have 3 informations in our little timer. So we have the robot motion from the RCS module, which will be always the same. We have the wait sec, which is also always the same, but this wait for signal is dependent on the performance of your computer. And it's dependent on the speed of the simulation. So at the moment, we're running it x1, but if you make it faster, maybe to 5, this wait for might vary. So you can see that the RCS output is still the same, 7.152 seconds, but here the wait for signal changed because the performance of the computer took more time to calculate that, and therefore it's just a little bit slower. What I want to say by that is you can fully trust this robot motion at all times because it comes from the RCS module, and it will also be just that if you run the same program on a real controller, but never really trust this wait for statements in your cycle time. Let's put simulation speed back. Now we want to have a closer look at what happens when I change the low data of the robot. So if I go back to jog and go to my tool data 1 to the settings, remember we had 20 kilograms in our tool 1. If I now change that to the full payload of the robot, so 120, it will change the inertia, but also if I play again the program, you will see that the robot motion time coming from the RCS changed. So at the moment we have 0.2 seconds slower movement that the RCS gives us. So this is really changing with the mass and the inertia that you put into the data, the low data here. Let's set back the simulation again. And let's enter here 300 kilograms, so way over the maximum payload of the robot, and play the simulation again. We will get an error message that actually the motor holding torque A3 was exceeded. So you have an overload of our KUKA robot, and this is the same as KUKA load will give you as a result. So let's set back the simulation, put back in our 20 kilograms of the robot gripper, and reset the simulation. And now we want to use some other output values that I stated before. So starting from the home position here in the jog mode, I want to now output this out signal 17, set output. And I will go to the statement properties and now enter this 17. And you will see that here it changes the action to a trace on and off with the material red, so red color. And if I play this from the home position, you will see displayed the trace of the TCP tool 1, how the robot is moving here. So this can help you to see and to visualize what the robot is doing. In addition to that, we can now change the signal to the swept volume, so the 81. And you will see that it has to restart the simulation. And now if I press play, the robot will directly show you or visualize what volume is he using to actually fulfill your task. So you can see where there might be some collisions, where you can put objects or where better not. Let's set back the simulation and change the signal back to 17. So we have a trace again. Now we want to add some more KRL expert programming statements. For this, we want to use a linear movement after our circ movement here, or after we have this wait second, so we actually put down our part. And we will now go to this expert programming drop-down menu and go to lin expert. In this case, it will just call our new position, so 0.5, and the position of the 0.5 in the statement. But we want to use a relative movement. So in this case, in the statement properties of the point, I will just click here on this relative and make a tick in the box. It will change the look of the point. And now we can now say in which direction to the last point, so 0.4, there should be a movement. In this case, it will go from x100, y100, z100. But in this case, we just want to go up. So I'm going to make x0, y0, and z500. And I don't want to change the orientation of the robot, so I have to use the KRL definition for that. So the turn of A will be 0, the degree of B will also be 0, and the degree of C will also be 0, so that we just have a movement upwards. What will happen if we do that and press play? It will do the same path as we've seen before, but now goes down to 0.2 and to 0.4, and now will do exactly that linear movement that we said it should do. So if we go to our measurement tool here and have a look at the point, which is approximately here, to the 0.4, we will see that it's about 500 millimeters. So I might not have taken the end of this relative movement, but it's the same way as you can program real KRL code also works here. In addition to that, we can also calculate points. So for instance, I want to change the point 1 that is currently up here, and I want to put it further down. So I can go after my timer statement, and now here in the logic, go to an assignment. In this case, it just sets the variable var to 0. This is not what we currently want to have. We want to change it as that the position, so xp1, the position of point 1 in z, so point z, will be a new position of p1, so xp1 of z minus 200 millimeters. And if I now press enter, it will write this KRL statement in my program. Let's have a look what happens. it takes my point 1 but sets it 200 millimeters further down and then approximates this point. So even though in my simulation it still appears up here, it will calculate a new point down there. And with that, you can do really nice stuff, for example, shift bases. So this is the next thing that we are going to do. Remember, we positioned our base 1 on the floor before the robot. So I'm just going to visualize that. So robot base. The base 1 is here. And now what we're going to do is write another assignment after our home position, which is still in base 0. We're going to go to another assignment and say here too the position of my base 1. So base data 1 dot x will be my base data 1 dot x plus 200. So in this case, it will shift all the points in x direction, and I will fail to grasp my part because my point 2 is now shifted 200 millimeters in front of the original base. If I reset the program now, my base will jump back to the original position. You can do also other assignments. If you want to define a new base through the program, you can do this also in the logic, where you have a set base or a set tool option. If we want now our robot to repeat this program over and over again, we can use a logic tool also here. For example, in the loops, an endless loop, and we can now select all our points and put it inside of our loop. I will also add my timer in this loop. If we play this again, it will do this over and over again. So the first, and now my base shifted, so I have 200 millimeters up front and it will do a new shape. But it will go to my original home position because this is in relation to base 0. And you can see that it iterates over and over again until I will run out of the reach of my robot. You can have a look at this when this happens. And it adds always these 200 millimeters to my point 1. So here I cannot reach it, and it tries to go now somewhere else, somewhere here. And so I get my error message that stop due to a software limit switch in A2. This happens if you use this increment of the space at the end of your program here. In addition to that, you can see that the cycle time was faster or slower depending on how far the robot is, and it also changes during that time. Now, actually I don't want this loop anymore, or this iteration, so I'm just going to select everything and put it out of my loop statement and delete the empty loop. And I will also delete this shift in my base data 1. And now I want to show you another beautiful feature of the KUKA Sim add-on, which is the trace diagram. And for that, we have to collect data in this trace group. And if we click on the trace settings, we can have a look at different channels. For example, our first group or channel will be our axis position, and our second channel will be the TCP velocity. We can have up to 2 groups here, and if we want to visualize that, we have to click here on this trace diagram, and it will open a new output window down here. We can make it a little bit bigger. And if I run the program now, it will generate me the position and a nice visualization of my TCP velocity and of my different degrees of my axis. And the best part about it is that I can jump back. So if I want to have a look, where do we have this high speed at the beginning, I can go back and see, okay, it's just after the start from the home position, and the robot will jump there. I can also see the other heights of this movement, or when we're specifically fast here on the way back to the home position. And it also puts out the value, how fast I'm currently, in millimeters per second. So this is a very nice thing to visualize that. And a nice, beautiful part is that when I collected once this data, I can now switch maybe from the axis position to the axis acceleration, and it will output me the same thing, so I don't have to run the program again, but I will be able to see, okay, where is the biggest acceleration of my axis 4 or maybe the axis 6 here. Or I can also let me show some other nice things, for example, my TCP acceleration. And I can see, okay, we don't have any acceleration here in the middle, it's 0, but we have some specific accelerations at the end, and it's braking at the end, so a deceleration at the end before the home position. With that, I can now optimize my program. So if we go back to the TCP velocity and the axis position, I can see that at the end, we are stopping after my relative movement, which is not very smart from a programming perspective. So I will set back the simulation, go to my relative movement and the statement properties here, and I can now approximate my position, for example, with this CEDIS statement. You can read that in the documentation of the KRL code. And if we run again the program, it will generate a new diagram here. And now it approximates the last point. Here the speed is not reduced to 0, but it actually accelerates through until we brake or deaccelerate again before the home position. If I go back to my output, we can have a look at the cycle times. So we have a slight reduction from 7.69 seconds to 7.48 seconds. And with that, you can incrementally now change and optimize your program. You can have a look at the trace diagram. For example, if there is a big change in here axis 6, the robot is only that fast how the slowest axis. So in this case, we have a big movement in axis 6. We might optimize this between our point 1 and our point 2. So if I maybe select my point 1 here and change the rotation of the whole thing, set it further down and touch up this point, I will now be able to see if this makes a change. We have a way smoother axis 6. And if we have a look at the output window at our cycle time, we also reduce the cycle time now by almost 0.5 seconds. So we have a real improvement right here. And like that, you can step by step improve your program, and you have the whole visibility via this trace diagram. A last beautiful thing about this trace diagram is the energy consumption. So if you select the power consumption in channel 1 and the energy consumption in channel 2, you can see how much just for this movement the robot will consume, and it's the same values as you would get from the controller. So if the controller supports this energy consumption monitoring, it will also do in KUKA Sim. So here we will use 3.9 watt hours, and we can also see the peaks where we have the biggest consumption. So you can also see that it's always while accelerating. So again, we could change the statements of our point, or the options of our point. Maybe we can reduce the acceleration here to 50% and also reduce the velocity to maybe only 50%. This will have an impact on our cycle time, but at the moment we care more about the energy consumption. So I will change also here the velocity, reduce it. Let's have a look if this has an impact on our energy consumption. So if I have a look back here on the total of my energy consumption, I reduced it by 0.5 watt-hours just by reducing the speed and the acceleration here. And also you can see that the peaks are way lower. So now I can continue and see where was this big acceleration. Okay, in my circular movement, I can reduce here also the velocity to 0.5 meters per second and run the program again. Now the robot is looking like he's moving in slow motion, but if I look again on my power consumption or energy consumption, I can see that I also drastically reduced now the whole energy consumption by 1 watt-hour to now 2.44 watt-hours. So this has a great impact on the overall costs of your robot if you are optimizing your layout or the path of your robot while offline programming. The last thing that I want to show you is how can you now take the whole project as you set it up to a real controller. First, you can save this setting as you did it right now. So I'm just going to save it. And now if you go back to the Home tab, we have the configuration, transfer configuration onto controller. This will be the topic of another video. Or we have this button, Export Project. If we click on this, it will enable us the export to WorkVisual. So if I just click Export here, and now go again from our File Explorer to our Documents, Visual Components, 4.8, then My Projects, you will find a KUKA Sim Intro V1 WorkVisual project. And if I double click on that, it will open WorkVisual if you have WorkVisual installed on your computer. So you can see the configuration that you have with your KRC5 cabinet and the robot that you added. Then if we go on the files and we go on the cabinet and the KRC R1, we will have the MADA and the same machine that configuration as we saw before. And in addition, if we go to Program and we go to our main SRC and double click on that, we'll find exactly the same program as we have done offline programming up front. So we have our home position, we have our timer, we have our PTP points. It's now all kind of is not collapsed, but you will see that it's exactly our program with our out signals. And from here on, you can now transfer it to your real robot and actually generate the code and start the commissioning process. If you just want to export some little programs out of Visual Components with the KUKA Sim add-on, you can go to Program of the robot, then go to the main, right-click on that, and start the Export KRL, and it will enable you just to export this current program. I hope this was helpful. I hope that you had a good video and you learned about first the basic configuration of the robot with the base and the tool management. Then in addition to that, the basic programming and the expert programming with the relative movement and the calculated points and bases. And in addition to that, the tracing function with the energy consumption and the point optimization. And last point was the export to WorkVisual, so you can now continue with the commissioning of the robot. Thank you very much for listening and see you in the next video. Bye!